Let's talk about Saturn. Now, has anybody in here not heard of the planet Saturn? Hands real high. Get yourselves recognized in front of everybody. This is why we're talking about this subject tonight. Because Saturn arguably is one of the most, if not the most recognizable object in our solar system. I mean, it is an awe-inspiring thing to look at. We all know what it looks like when we see it. It's very recognizable. And arguably, other than the moon, Saturn is the #1 object that people think of when they think about astronomy. So if you talk to anybody about astronomy, the first question they're going to ask you is, do you have a telescope? And then the second question they likely will ask you is, have you seen Saturn through a telescope? I saw Saturn a couple of years ago. I was at an observing session, and it's an amazing thing to see. You see the planet, you see the rings, and you see the little dot over there, that's the moon Titan. And for me, the reason why we're talking about this tonight is because it's one thing to know where these objects are, and to see the little dot in the sky, or to see it through a telescope. It's another thing to be able to visualize in your mind what's going on some of these worlds. And it's really fascinating when you study astronomy, what some of these places are like, what some of the planets are like, what some of the moons are like. They're just alien to us. I mean, something that's totally foreign from what we recognize and what we experience every day on Earth. So the purpose of tonight's presentation on Saturn is to enhance your understanding of this planet and hopefully get you to a point where you never look at it the same way again. So that when you look at it through a telescope, you can visualize what's going on. And you can see just how violent and dynamic and really exciting a system Saturn is. Now, Saturn is very easy to find. You can find the Big Dipper. What I do is I just draw an arc from the handle of the Dipper. Arcturus is one of the 5 brightest stars in the sky, very easy to spot. And you just draw an arc down to Spica, and Saturn's right there. Now, it's not out this time of year because we're getting into the winter season. So, but in the spring and summer, it's very visible. So, easy to find. It's the second largest planet in our solar system. It's about 9.5 astronomical units away. An astronomical unit is the distance from the Earth to the Sun. And it's what's called an oblate spheroid. What that means is it's rotating so fast that it's actually squashed a little bit at the poles and bulges at the equator. So if you've ever been to a pizzeria and you see them throw the dough up in the air and it flattens out, same type of thing is happening on Saturn. It's basically a great big ball of hydrogen and helium. You can see it's quite a bit larger than the Earth. The radius at the equator is about 9.5 times the size of the Earth. 96% hydrogen. Most of the planet is hydrogen, a little bit of helium, and then some other trace elements. It has a dense rocky core at the center that's several times larger than Earth. But what's interesting is the mean density of Saturn is actually less than water. It's about 0.68 grams per cubic centimeter. Now what that means is, if you had a bathtub or an ocean big enough, you could literally plop Saturn down in it and it would float. It's the only planet in our solar system that's less dense than water. So it's a great big ball of gas. It's big, it's beautiful, and it's full of hot air. Kind of like Kim Kardashian. But unlike Kim Kardashian, Saturn has a ring. In fact, it has a lot of rings. That's what we're talking about tonight. Now, a person on Saturn would weigh less than they would on Earth, even though Saturn's quite a bit larger and has a lot more mass. So it's an interesting planet.
Why don't somebody weigh less because it's further away from the Sun?
Okay, it's a gas planet. You can't stand on it. It doesn't have a solid surface.
Yeah.
But if you could stand on it, hypothetically speaking, because it's not very dense, your effective gravity on the surface would be less than it would be if you were standing on Earth. That's why you would weigh less, even though it's so much larger and it has so much more mass. So it's not just the matter, it's the distribution of the matter that determines what your effective weight would be when you're standing on this object. So, did that answer your question? More or less? Yeah. Yes?
Like if you were on the moon, you would be a whole lot, you would weigh a whole lot less.
Right.
1/6.
1/6. You have a question?
Yeah,
you were saying that the core was about twice the size of Earth, and that it's pretty dense and everything like rock core.
Mhm.
My question is, considering the core, I'm trying to figure out, as in Earth.
Okay.
Earth, I'm not really sure if the atmosphere is considered Earth, if you know what I'm saying.
Right.
It's the hard core surface, and I'm curious why that the gases are necessarily considered part of Saturn, opposed to saying Saturn is twice the size of the Earth with a huge atmosphere.
Okay, here's the way I like to think about it. Draw an analogy. The Earth's atmosphere in comparison to the solid part of Earth. Take a basketball,
Right.
dunk it into a bucket of water, pull it out. The water that's left on the basketball would be analogous to the atmosphere on Earth.
Okay.
So effectively, in comparison to the rest of the Earth, and correct me if I'm wrong, Bill, the mass is quite a bit, I mean, it's virtually negligible. Saturn is like a great big ball of cotton candy, where the stick would be the rocky core, and then all the cotton candy around it would be the gases of the planet. So you have you do have a dense rocky core that's about 9 to 20 times larger than the Earth.
Mm-hmm.
But you've got so much gas enveloping this rocky core that when you factor that into the dimensions of the planet, effectively you have this very, very light and less dense object that actually is less dense than water. So yes, you can still have a dense core at the center of a planet, but when you factor in all the gases that are enveloping that core and the dimensions that result from the expansion of that object, it actually effectively, the object as a whole, effectively has a much, much smaller density.
Right, but I mean, I guess I'm just thinking along the lines of, if I was going to Saturn and I was going to land a spaceship on Saturn, I could tell the people with the spaceship, I'm now entering the atmosphere, of Saturn, which, I mean, I understand that would be the atmosphere, but until I actually hit the hard ground, I would never tell them that I've landed on the planet.
Right.
And so it would seem to me that
you would continue to descend through layers and layers and layers of gas, and the pressure would get stronger and greater until eventually your spacecraft would get crushed.
okay.
And then, and if you could descend even further, the temperature would get so great that you would be fried. The interior cores of these gas giants are environments that are so foreign, so alien to us, because you're descending through all these layers of gas, and the pressure just keeps getting greater and greater and greater.
Okay.
So it's an interesting question because yes, it's a gas planet, and you can't land on it. But if you were to send a probe or something man-made to a planet like Jupiter or Saturn, you would descend through the cloud layers, and as you descended further and further, the pressure and the environment would get so great that things would change. Things get really weird. Hydrogen, which is a gas, starts to behave like a liquid, and then as you go further, it starts to behave like a metal.
Okay.
In fact, the most abundant metal in the solar system is liquid metallic hydrogen. But we'll save that for another presentation.
Okay.
All right. The data for the analysis of Saturn came from a space probe called the Cassini-Huygens mission. In the late 70s, the Voyager spacecraft did a flyby of Saturn on its way to the outskirts of the solar system. Took some pictures, went into National Geographic, and actually for years when I was a kid, I had a poster on my wall of a snapshot of Saturn from the Voyager mission. This mission was different. Cassini was a probe that was launched, sent to Saturn, and orbited the planet, basically stayed there for several years and just kind of hung out. And here's kind of a timeline. It was launched in '97, got to Saturn in '04, stayed there for several years, actually landed a probe called the Huygens probe on the surface of Titan. It's the only other alien moon, other than our moon, to be explored in the solar system. And it's the most distant object beyond Mars to have a probe land on it. So it's a significant accomplishment. This mission went until '08, and then they extended the mission a couple more years. It was called the Cassini Equinox mission. And then in 2010, they extended it even further. And right now, the probe is still there. It's made about 80 orbits around the planet Saturn, taking data, taking pictures, doing analysis, sending all the information back to Earth, and scientists are analyzing the data, and this is helping them really gain an insightful understanding of Saturn, the planet, the weather, the rings, the moons, everything, the entire system. So that's kind of the foundation of tonight's presentation, the findings of the Cassini-Huygens mission. Now, I like this graph because it illustrates just how challenging it is to get a probe to the outskirts of the solar system. Guys, Saturn is very far away. Here's the way I like to think about it. Take the sun, scale it down in size to the size of a bowling ball, all right? We're going to model the solar system. I go to Memphis Grizzlies games sometimes. The width of the basketball court would represent the distance from the sun to the earth, okay? Take that distance, cut it in half, and add on to that, you get from the sun to Mars, roughly 1.5 Memphis Grizzlies basketball courts, okay? Take that distance, multiply it by 3, and you get from Mars out to Jupiter, all right? Now take the distance from the sun to Jupiter and double it again, and you get out to Saturn. Saturn is so far away from the sun that it's a miracle that light from the sun actually reaches Saturn to the point where we can see it. So, to get a probe out there, it's not enough just to have a big rocket engine, all right? Watch this. You launch the probe in '97. You slingshot it around Venus. Then you slingshot it around Venus again. You slingshot it around the Earth. And what that means is we're taking advantage of the gravity of Venus and the Earth to bring it out to Jupiter. And then you use Jupiter's gravity to fling it out to Saturn. All right? This phenomenon is called gravity assist. And this is one of the ways, this is the fundamental way that we get space probes like Cassini out to Saturn. We don't just launch them like we see in science fiction films and blast them out there and hope they get out there. Chemical rockets are very inefficient, and they're not sufficient to get out to the outskirts of the solar system. So I just want to point that out. It takes Saturn about 30 years to orbit the sun. Yes?
How much, as far as, I know that if you get out in a certain area in space and everything like that, you don't need very much energy to actually get something moving. So, and assuming that we can get things moving as it is now at a fairly fast speed, I'm curious, using the slingshot effects and everything like that, how much extra speed does that, do you know?
Off the top of my head, I don't. The details of how this works, you're right. In space, there's no resistance like there is in an atmosphere. So once you get something moving, you can get it moving really, really fast, faster than a speed, a rifle bullet. It's not like the probe will lose momentum.
Right.
Once it's moving, it's moving. As far as the specifics of how much additional speed or momentum is picked up, I don't know.
Okay.
But I know that they use the gravity from other planets to get out there. So.
But look how many years it took.
Took a while, didn't it? 7 years to get out there from the launch date. So now, was all this necessary? I don't know. I think maybe, hey, what the heck? Let's go check out Venus. Haven't seen any snapshots of sulfuric, acid rain in a while. So why don't we check that out on the way out to Saturn? So. But yeah, this is an important concept when we're getting to the outskirts of the solar system. Let's talk about Saturn's weather. This is where it gets interesting. Saturn has some of the most violent weather in the solar system. We're talking about wind speeds up to 1,000 miles per hour, faster than the speed of sound. We're talking about lightning that can be as much as 1 million times stronger than lightning on Earth. Storms larger than the United States that last for years. It's a gas giant. There's a lot going on. There's a region of the planet that the Cassini probe has been exploring for years now. It's called Storm Alley. It's actually in the southern hemisphere, about 35 latitudes south of the equator. And you can see a lot of activity going on in this region, very similar to what we see going on Jupiter. In fact, Saturn, in a lot of ways, is more dynamic than Jupiter is. So we see a lot of this storm activity happening here, eddies, plumes, ovals. We see storms forming, merging, becoming bigger storms, dying off. They're created. They die off. We see lightning storms. So this is an area of the planet that is really fascinating astronomers right now. And talking about lightning, back in November, Cassini observed a lightning storm, flashes that lasted less than a second in this lightning storm, but the bolts themselves were wider than half the width of the state of Arizona and had enough energy released to fry the entire state of Tennessee. And this lightning storm lasted for 8 months. So we're getting storms tonight. Imagine walking out and having lightning this powerful. Pretty nasty stuff. Now, let's talk about some other features that have been observed recently on Saturn. Back in the early 80s when Voyager flew by Saturn, it took a snapshot of the North Polar region and it noticed this perfect hexagon shape right over the North Pole. And for years, scientists didn't really know what that was. It was just kind of a bizarre feature, a geometric shape in the North Polar region of Saturn. Well, it turns out Cassini gets there and starts taking images of this storm, and it's still kind of a mystery, but it's a North Polar vortex that could literally, well, okay, you could stuff 4 Earths inside of this North Polar vortex. Each side of this hexagon is 8,600 miles long. That's longer than the diameter of the Earth. 60 miles deep, and you have clouds racing around this racetrack at over 100 miles per hour. It was there in '79 when Voyager passed by. It's still there today, so it's been there for at least 30 years. Just a bizarre feature in the North Pole of Saturn. And if you were looking inside it, it would look something like this. You see these clouds just kind of racing around this racetrack. Again, each one of these is wider than the Earth. You could stuff 4 Earths inside of this hole. So it's just a fascinating and bizarre feature on the North Pole of Saturn. And it's still there. It's been there for over 30 years. In the South Pole, we see a storm with a clearly defined eye wall. Only other storm in the solar system. Jupiter has a red spot, but it doesn't have an eye wall. Earth has hurricanes. We have a really, really nasty hurricane like Katrina or Camille. You know that the nastier the storm, the more clearly defined the eye wall is. Well, on Saturn, there is a south polar storm that has a hurricane-like structure. It's not exactly a hurricane, but it behaves kind of like a hurricane. And it has a clearly defined eye wall, which means scientists can literally probe into the eye wall and do some research on the interior of Saturn. It has winds blowing in excess of 350 miles per hour, clouds that are 20 to 40 miles higher than the cloud structures we see for hurricanes here on Earth, and 5,000 miles wide. So imagine a hurricane that stretched from New York City to Baghdad with winds in excess of 350 miles per hour, lasting for years, destroying everything in its path. That gives you an idea of some of the storms that are happening on Saturn. Not a good time. All right. We can't talk about Saturn without talking about the rings. So, Galileo was the first scientist to actually look at Saturn. Saturn's been around for a while. I mean, it was discovered back, before, in BC times. The ancient Romans and Greeks saw the sky, the Saturn in the sky. But Galileo was the first one to actually look at it through a telescope. And he saw a structure that he didn't quite understand or recognize. And he couldn't describe it in words. But like all astronomers, he kept a journal. So he drew a diagram in his journal of what he saw. It was kind of a spherical shape with 2 lobes on the end. And at first he didn't know what that was. Maybe 2 moons that were adjacent to the planet. Didn't exactly know how to describe it. But he really is the one who discovered the structure that would become the rings of Saturn. Now, 45 years later, Christian Huygens, a Dutch astronomer, had a more powerful telescope than Galileo, and he was able to see more details. When you see more details, as technology improves and evolves, then you can make more, you can make more data-driven observations and conclusions. So he was the one who figured out that that structure was actually rings, and it was a disk of rings or materials orbiting the planet Saturn. He also discovered the moon Titan, Christian Huygens. So what are the rings? There are 7 main divisions of the rings discovered, and they just named in alphabetical order, in the order in which they were discovered. And inside of each of these 7 main rings are thousands of smaller ringlets, all right, that are made up of trillions and trillions of small dust and ice particles. 35 trillion tons of dust and ice, mostly water ice. And it's estimated that it contains about 36 million times as much water in the rings of Saturn as there is water on Earth. Now, the particles range in size from a grain of sand to as big as your house, all right? And they're just flying around Saturn. Saturn's gravity is whipping them around 20 to 40,000, at speeds up to 50,000 miles per hour, or 15 times the speed of a rifle bullet. To give you an idea of how deadly this is, if you were to fly a spacecraft into the rings of Saturn, and a particle the size of a grain of sand were to hit your spacecraft, it would be like getting blasted with a shotgun at point blank range. The rings are incredibly wide, 175,000 miles, 20 Earths. So take 20 Earths, stack them side by side, and that would be the width of the rings of Saturn. Now, what's interesting is how thin they are. They're only about 60 feet thick. So you've got 175,000 miles worth of width and only about 30 to 60 feet of thickness. That's like 1 or 2 stories in a modern day building, or the height of your house, 1 or 2 of your houses.
Is that our house or Mitt Romney's house?
That would be it wouldn't be Mitt's house, I don't think. But anyway, they're paper thin. So imagine a sheet of paper the size of Memphis. And that gives you an idea of the dimensions of the rings of Saturn.
So the spacecraft that passed through the ring was really lucky.
Yeah. You wouldn't want to pass a spacecraft through an area where there's actually particles. You want to put if you were going to send a spacecraft into the rings, you want to aim for one of the gaps, either the Cassini gap or one of the other gaps, where there isn't a lot of material flying around.
You can match the speed, I guess.
50,000 miles an hour?
Well, with orbital speed, if you had an orbit around it, it's kind of eased it through.
Or just be just below, or just
Yeah.
above. There you go. Not be right there where all the particles
It would soon get into it.
are. Yeah. They're named in alphabetical order from when they were discovered. But this is kind of, from the surface of the planet out, this is the order of the rings. So you've got the 3 main rings. You've got the D ring, which is barely visible. And then you got the thinner F ring, and then the E and the G ring, which are like diffuse rings. So breaking it down, this is the innermost ring, very faint. The ones in red, if you're looking at Saturn through a telescope, or a spacecraft is taking a snapshot of Saturn, these are basically the 3 main rings that we're all used to seeing when we look at the planet Saturn. So this one is a thin ring, and then the G and the E rings are just very, very diffuse material, very, very wide, and barely visible. So when you think of the rings, there's 7 main rings, but these are the 3 that count in terms of being visible and being able to be seen consistently. So, but each ring has a different personality, has a different constitution, has a different types of, in terms of transparency and in terms of, material type. But, there are divisions, clear divisions in the rings. There's a lot of data on the rings. We could literally talk for hours about the rings and how they're broken down. Yes?
Is the D ring the same as the crate ring?
That's the innermost ring. That's a good question. I don't know.
I've got some books that refer to the crepe ring, but I don't,
Do you know if it's the innermost ring?
I believe it is the thing, the most transparent one.
Yes, if it's the most transparent
Yeah.
one. Well, it's either, okay, the most transparent ring is the E ring.
Well, it's the innermost.
Okay, it's the innermost, yeah, then yes, it would be the D ring. I don't know the name though, it's a good question. You have different divisions between each of the rings. So I don't want to talk about this in a lot of detail, but yes.
Go ahead now, when we get through talking, I'll ask the question.
So just kind of a snapshot of what it would look like. You have trillions of icy bodies, mainly water ice, spinning around the planet, colliding into each other, constantly pulverizing each other and making the particles more and more fine. Another snapshot of kind of what it would look like, icy particles again, just colliding into each other. Now, what's interesting is this material is being pulled around by the gravity of Saturn. Each particle is attracted to itself. As it moves, there's this tendency for these particles to want to compress and form spherical bodies like small moons. So you've got the force that wants to compress and form larger bodies, but then you've also got the gravity of Saturn that wants to rip them apart. So these two forces are in equilibrium and constantly balancing each other out, causing these materials to just keep basically swarming around and forming these rings instead of clumping into larger material to form larger bodies. Now they're constantly pulverizing each other, and the particles are constantly getting finer and finer with time.
Why don't they homogenize?
Why don't they homogenize?
The rings,
Or come together?
yeah.
Okay, there's other forces at work too. We'll talk about that. There's smaller moons that are creating gaps within the rings and sculpting them and shaping them. We'll talk about that in just a second. Shepherd moons. Yes.
I guess now since you're in this part, do the rings all rotate around or orbit around the planet in the same direction? Okay.
Yes.
Do you know if the clouds around the planet all rotate in the same direction?
That's a good question. Yeah, but at different speeds.
Okay.
Like Storm
Okay.
Alley is at a different speed than some of the other cloud patterns,
Okay, I got you.
which is why there's more violent weather in that strip that we talked about.
Mhm.
So, yes, but to answer your question, the particles do go around at the same speed.
Okay.
But, I mean, the same direction,
Okay,
not the same speed.
right.
The ones that are closer to the planet will go faster, the ones that are further away will go slower.
No, okay, gotcha.
Okay, now the origin of the rings is still a mystery. There's a lot of different theories. One theory is the rings formed when the planet Saturn itself formed. There's other thoughts. One of Saturn's moons maybe got too close to Saturn, and the tidal forces of Saturn's gravity ripped the moon apart and formed this disk of material. Maybe two moons smashed into each other, and the material from that collision fell off and got pulled into Saturn's gravity. A nearby comet came by, and the gravity of Saturn snagged that comet and ripped it apart. We really don't know how the rings formed. We also don't know the age. The thinking is the rings of Saturn are fairly young because all the gas giants have rings, but Saturn's rings are the only ones that are bright and visible. Very, very bright. In fact, if you were on the night side of Saturn, it would be so bright that it would be several times brighter than a full moon on Earth if you were on the surface of Saturn. So, but we don't know the age and we don't know the origin. But the thinking is they're fairly young in comparison to the other gas giants because the rings of the other gas giants are so thin that they've eroded over time, and Saturn's are still fairly thick and bright and well-defined. Now, what's interesting is when you start looking at the way the rings of Saturn interact with the moons. This is just kind of a cross-section going from the innermost D ring, then the three main rings, all the way out to, you can see the E ring here, okay? Very large, but also very faint and very diffuse. And within this E ring are some of the moons of Saturn, some of the regular moons like Mimas, Enceladus, and then a couple of these other ones. And then as you get beyond the E ring, you've got the more distant moons like Titan and some of these other ones. So, and then you've also got smaller moonlets within the ring system itself that are really interacting with the rings. So Saturn is a planet and a system that not only has a ring structure, but has a moon system that is interacting with that ring structure. So, and one of the discoveries that's kind of exciting from the Cassini mission was the discovery that there are actually mountain ranges within the ring system itself. So we talked about how thin the rings are, 30 to 60 feet, 1 or 2 stories in a modern day building. But there's actually at least 62 what are called moonlets embedded in the ring system. And they cause portions of these rings to be elevated to mountain ranges that can be they can be actually taller than the Alps. And this is a snapshot of the F ring from the Cassini mission. How does this work? Well, you've got the ring particles here, and then you've got this moonlet body here, basically moving through just underneath the plane of the ring, causing the particles to be elevated as this moon sweeps through. And that's how these mountain ranges are formed within the ring system. In fact, in Saturn's A ring, the small moon Daphnis has carved out a vertical peak that's over 2.5 miles high. So it's kind of an interesting finding from the Cassini mission in terms of the interaction of the moons or the moonlets with the rings of Saturn. Now, shepherd moons. Like the name implies, there are smaller satellites that interact gravitationally to keep the rings in line. This gets back to your question. Why don't they come together? Because you've got satellites like these shepherd moons that are interacting gravitationally with a smaller ring and basically sculpting them and keeping them on track, so to speak. So this is an actual image of Prometheus and Pandora and the F ring. As these moons orbit around the F ring, they keep the particles, basically herd the particles like a shepherd herds sheep. So that's the idea behind shepherd moons. And that's really how the F ring is sculpted. Now, there's a lot of moons. We're going to go through every single one of them tonight, and we'll be here until Monday morning. No, we're going to talk about 2 of them. And you know, when you talk about some of these planets, it's fascinating to study the planets, but really the moons are where the action is. The moons are fascinating worlds. And this is where, to me personally, astronomy just gets really exciting when you see what's going on some of these alien planets. So let's talk about a couple of these. First one we're going to talk about is a moon called Enceladus. All right? Now, this is not a very big moon. It's the 6th largest moon of Saturn. It's only about 300 miles in diameter, so it's very small. But it's made up, its surface is almost entirely frozen water ice. So in terms of reflected light, it's one of the brightest objects in our solar system. It reflects almost 100% of the light that shines on it. And it's a geologically active world. We see large plumes of water vapor and ice being ejected from the moon. You can see a snapshot here of kind of what Enceladus would look like relative to the Earth and the Earth's moon. It would easily fit within the states of Colorado and Arizona. So it's a small moon. But we see an interesting phenomenon happening in the south pole of Enceladus. And Cassini actually has taken images of this. We're all familiar with volcanic eruptions on Earth. When a mountain blows up, you have hot magma that comes up from the surface. The same type of thing is happening on Enceladus, except instead of hot magma or lava, it's actually water ice shooting up geysers, like you see at Old Faithful in Yellowstone. And there's several of these things that are actually shooting this material hundreds of miles into space. And this is kind of what it would look like if you were on the surface of Enceladus. So you see these tiger stripes here that are shooting these geysers, these large plumes of water vapor. It's water vapor that freezes instantly and literally shoots this frozen water ice out into space. And that actually is one of the things that contributes to a lot of the material in Saturn's E ring. So here's a snapshot from Cassini. Here's another one. This was observed in November of 2009. And you can see these geysers that are shooting, blasting these water plumes hundreds of miles into space at over 1,400 miles per hour. And what causes this to happen? Saturn's a massive planet, has a lot of gravity, and Enceladus is a small moon. So it's caused by gravitational tidal effects as the moon orbits the planet Saturn. Sometimes it's closer in its orbit, sometimes it's further away. So when it's closer, it's constantly stretching and pulling the planet. And that's causing the interior of the moon Enceladus to have rubbing and friction and heating that causes this water vapor to shoot up. It's a little bit like having a water balloon and just kind of squeezing it. You know, if you can kind of picture that in your mind. That's what's happening when smaller moons like Enceladus orbit these larger gas giants. And that's what's causing Enceladus to be so geologically active. So, and the term is called cryovolcanism because it shoots water ice into space.
Do they think that that might cause it to collapse upon itself or anything like that, do you know?
Like destroy the moon?
Yeah, eventually if you're shooting all your water out and it's going out into space, then you're not going to have any water, and I would assume the gravity would cause the outer ice to collapse upon itself possibly, or something like that.
Yeah, I mean, some material is being liberated, it's escaping the gravity of the moon. So yeah, you could argue that over time it's losing mass. I would think it would be a while though before it loses enough mass where it would run out of water.
No.
The reason why Enceladus is so fascinating, that's an interesting question. The reason why Enceladus is so fascinating to a lot of scientists and astronomers is it's because it's one of the sources of water, potentially one of the sources of water in our solar system. And of course, it's all about the water, right?
Right.
Why water? Because water, if you follow the water, if you find liquid water in some of these worlds, then there's a possibility you might find life. So scientists are fascinated with Enceladus. In fact, if you were to make a list of the 7 wonders of our solar system, Enceladus would be on that list, and along with the rings of Saturn. And I would actually argue Saturn would have 3 of the 7 wonders of our solar system. But I think a lot of scientists, solar system planetary scientists today would agree that Enceladus would be on that list because of how active it is, how dynamic it is, and because it's a place where you could possibly find water.
In its travels, wouldn't it scoop up some of the water too?
You're traveling through the E-ring, and the diffuse material that makes up the E-ring actually comes from these geysers and these plumes from Enceladus, and it would fall back on the surface. So yes, you're absolutely right. Some of that material would actually come back onto the surface. It's a little like shooting a geyser up, right? First it leaves the Earth's environment. It leaves the environment when it shoots up, but then eventually gravity pulls it back down. Well, in Enceladus, you're shooting material out into space. It's being liberated from the gravity of Enceladus, but the moon is continuing to move through the ring and sweep this material back in. So yeah, you could make that. Yeah, you can make that argument.
So it's shooting water. The water is obviously above 32 degrees Fahrenheit then? I mean, it's liquid, right?
It's liquid in the core. When it gets shot up from the geyser, it instantly freezes because you're in the environment of outer space. So it's not being shot out as a liquid. It's actually being shot out as kind of a fine powder, almost like snow, like a snowmaking machine.
Fire extinguishers,
Right,
CO2.
right.
We were in college up north, and we were just moving around, but the temperature got to 20 below zero. Then we boil water in a big pan, right? And run outside and throw it up at people, and it would instantly freeze.
Right.
Is that the same
Analogy, yeah. Yeah, like if you were in Antarctica or in a very cold environment, like you were in college, you have a pot of boiling water, you throw it outside and it freezes instantly. Yeah, it's a great analogy. Same type of things happen on Enceladus. So yeah, that's exactly right. So, fascinating moon. Let's talk about Titan for a minute. Now this, of all the worlds in our solar system, to me personally, this is probably the most fascinating world. All right? Titan is the largest moon of Saturn. It's the second largest moon in our solar system. Only Jupiter's Ganymede is bigger. It's actually larger than the planet Mercury. It's the only moon that has an extended atmosphere in it. And the atmosphere's composition is interesting. It's made out of nitrogen and methane. It's a very dense atmosphere. It's about 10 times denser than the Earth's atmosphere. But it has kind of a deep smog-like environment. I mean, imagine Los Angeles on steroids. That's kind of what Titan's atmosphere is like. It's just a very, very, smog-like, very, very dense atmosphere. But the terrain of Titan is just incredibly fascinating. It's made of mountains that are made out of frozen water and ice and methane, and it has hydrocarbon lakes. And it's the only other world in our solar system that has liquids at its surface. So nitrogen, the dominant gas in the atmosphere, and it has liquids on its surface. Yes?
Do you think there were once dinosaurs on Titan? Because that's where hydrocarbons supposedly came from.
I'm not going to go that far. I don't think that's dinosaurs. I'll wait until primitive microbial life is discovered in the universe before I start placing my faith in complex organisms. So show me the bacteria. Show me the single cell organisms first. Then we'll get into turtles and rabbits and dinosaurs and other things. But that's interesting.
The
They're
bacteria,
organic compounds.
Fossil fuels.
the bacteria that can live at 30 below zero up to 250.
You know, what's chilly for us may not necessarily be chilly for some forms of life, primitive forms of life. So, but again, show me the data. Show me the results first. But Titan, dominant gas is nitrogen in its atmosphere. It's the only other world in our solar system with liquids on its surface. Not liquid water, liquid methane. Methane is a gas. Yes?
I thought Ion had liquid methane on the surface too.
No. Io has molten lava being shot up through volcanoes. Again, Io is similar to Enceladus, and that Jupiter's gravity is stretching it and pulling it tidally. And that's what's causing all the volcanoes to shoot up.
No.
But I'm talking about like a world with an atmosphere and actually liquids that can exist on the surface.
No, okay.
Liquids are very rare in the universe. Very rare. So we have water on Earth. On Titan, they have methane. Nitrogen, liquids, dominant gas. Titan is the second, okay. So Titan in a lot of ways is our sister world. If you're going to compare any other world in our solar system to Earth, it would be Titan. And what's fascinating to me is just to try to envision what it would be like to be on the surface of Titan. I mean, imagine an environment where you have an orange, reddish sky, you have mountains and cliffs and canyons made out of water, ice, and frozen hydrocarbons. You have a spectacular view of Saturn in the background. And then you have these lakes and these riverbeds and flowing liquids at the surface. Only the liquid is methane, which is a gas on Earth. It's not water, it's methane. Because the temperature on Titan is minus 300 degrees below 0 Fahrenheit, roughly. So it's incredibly cold, and the chemical property, the chemicals of substances on Titan behave very differently than they do on Earth. So you have all this terrain. You have rivers and lakes, mountains, and you have dunes. I mean, okay, so the Huygens probe landed here in January of 2005. And again, it was the only other world other than Mars to be explored outside of the inner solar system. So when Huygens landed, it landed on some kind of a weird surface that was kind of a cross between a liquid and a solid, almost kind of like a gooey, pudding-like substance. So you've got that on Titan also. So you've got all this terrain of liquid that just carves out channels and lakes, and you have coastlines. Similar to what you see on Earth, only water forms on Earth but liquid methane forms it on the surface of Titan. So you can imagine a scenario on Titan similar to being on Earth, where you have kind of a gentle breeze blowing, and you see the haze and the mist of the atmosphere, and you hear water, or you hear liquids lapping up on the shore, only it's liquid methane instead of liquid water. Now, liquid methane is not like liquid water. The properties of liquid methane are very different than the properties of liquid water. So, methane is a hydrocarbon, all right? Water is a good solvent. So you have basically H2O, a hydrogen, or yeah, you have two hydrogen atoms and an oxygen atom, so it's a polar molecule, so it's a good solvent. So here's the analogy. Imagine I had two pitchers in front of me. I had a pitcher of water, and then I had a pitcher of a liquid hydrocarbon, like methane, like you would find on Titan. And I dropped saltine crackers into each one of these pitchers. If you stir the pitcher of water, the saltine crackers are going to dissolve into the liquid water because water is a good solvent. But if you drop the crackers into the liquid methane or the liquid hydrocarbon and try to stir it, the crackers wouldn't dissolve because a hydrocarbon atom, methane, is basically a carbon atom with 4 hydrogen atoms, so it balances out really well and it doesn't dissolve things well. So you could literally drop crackers into a pitcher of liquid methane, pull it out, and they would still be crisp and they would still break. Counterintuitive to what we would think liquids would do to something like that. Yeah.
Is that based on the temperature that it would have to be? I mean, I'm assuming that it's extremely cold. I mean, the liquid methane. I mean, is that based on the fact that it has to be so cold to become liquid that makes it non-solvent, or is
No. The chemical properties are based on the molecules and how they're put together. Now, methane is a liquid on Titan instead of a gas because of the temperature. You're absolutely right. So, you know, it has less kinetic energy, so that the molecules tend to condense, if you will, and behave like a liquid. That's why methane is a liquid on Titan instead of a gas because of the temperature.
right?
But in terms of its properties as a liquid, totally different. It has to do with the chemical properties or the molecular constitution of methane. So if you compare water molecules to methane molecules, methane is a hydrocarbon. You have a carbon atom with 4 hydrogen atoms that make up one methane molecule. And because it's all perfectly balanced out, you don't have polar properties in the molecule like you would in a water molecule, where water is H2O. You have an oxygen atom with 2, it's like Mickey Mouse, right?
Right.
Oxygen, 2 hydrogens. So you've got a polar molecule that takes apart things really, really well. It's like little magnets. That's what water is. Water's like a little magnet.
Is there any liquid on Earth that, that is liquid because of the temperature that's not a good solvent?
Oh, yeah. There are liquid hydrocarbons on Earth. I can't think of one off the top of my head because I'm not a chemistry professor. But
Octane,
octane.
Okay.
gasoline, just
Gasoline.
do this at home with gasoline. Just try dissolving a cracker of gasoline.
Okay.
Gasoline.
So, on Titan, a methane is not volatile.
That's
No,
what I wanted
there's
to
no
know.
oxygen. Now, if you had oxygen on Titan, it would be. It would be very explosive. So, yes, Titan is fine because you have nitrogen and methane in the atmosphere along with a few other hydrocarbons. But you don't have oxygen, so it's not a flammable liquid like it is, or a flammable substance like it would be on Earth. The reason...
So it wouldn't matter if you had lightning.
Right. If you don't have oxygen, you don't have a chemical reaction. Now on Earth, methane is very volatile on Earth because you got all this oxygen around. So, yeah, Titan is fine because there's no oxygen there. So,
Well, it's there, it's just bound up with the hydrogen molecule of water.
frozen water,
Right, it's just,
right, it's not a gas, yeah, it's not a gas.
But as she said, if you had a lightning strike, if you had some heat source to liberate it, you could have.
If you had a heat source and you had oxygen, you'd
Yeah.
have trouble
Yeah.
on Titan. Absolutely.
Or not, wouldn't it?
So,
Based on the simulated landscape, we would look at that and we would say that the liquid methane would be eroding and creating the mountains and the rivers and the lakes.
it's carving out the terrain.
So it's not, it can't, if it's not working like water, then it's probably not doing that, right?
No, I mean, it's not a good solvent,
As far as erosion.
so the chemical properties are totally different, but in terms of its motion, in terms of its, in terms of its ability to move material and carve out features on the surface, whether it's riverbeds or channels, coastlines, and terrain, it's very similar on Titan as it would be on Earth. We have a water cycle on Earth. Titan has a methane cycle. So liquid flows. Anytime you have flowing liquid, you can see these features.
And the Grand Canyon wasn't formed because rocks are soluble in the water of the Colorado River. It's physical abrasion and sand that's formed still doesn't dissolve. It's two different things that aren't soluble in each other, like you were saying, that it's just the physical erosion, not chemical solubility.
It's the physical effect of the flowing liquids.
Would there be a possibility of lightning on?
I don't know if there's been any specific case of a lightning strike on Titan. Can I read up on that one?
It would be, a buildup of free
Yeah.
ions.
How fast does it rotate? Is it locked towards Saturn?
It is phase locked towards Saturn. Like a
Okay,
regular
well, you're
moon.
probably not gonna have any
We're
light.
not gonna have a lot of,
Okay.
a lot of
So
rotation.
it's a point.
Yeah. You also have dunes, hydrocarbon dunes, hundreds of miles in the equator region of Titan. Fascinating feature that Huygens observed. And then again, channels carved out by liquid methane, rock formations. On Earth you have silicates. So here's the analogy. On Earth you have silicates, bedrock, that makes up the physical terrain. On Titan you have frozen water ice, frozen methane, frozen hydrocarbons, and then flowing liquids. And rain. Imagine it raining methane. Methane rain. So we're in a rainstorm today, where it rains water. Titan has methane rain. Incredibly fascinating. Now, let's talk about methane rain, because it's not like rain on Earth. Because methane has a lower gravity, and because it has a thicker atmosphere, rain actually falls much more slowly on Titan. Drip, drip. And the raindrops are about twice as big as the raindrops on Earth. And they're kind of gooey, kind of almost like snot falling. All right? And if it hit your skin, it would be ice cold, instant frostbite. But it has Titan has a cycle, a rain cycle, similar to the rain cycle on Earth. Except on Earth it's liquid water, on Titan it's liquid methane.
Does that mean?
That is an illustration.
Does that mean it's heating enough to vaporize and then come back and go to cloud formation and then come back
It
down?
has a rainy season.
So it actually goes into a vapor state?
It goes in, yeah, that's an interesting question. Yes, it would have to. There are times when Titan goes through a rainy season where there has to be an evaporation type of effect forming these clouds that are raining methane down on the surface. So, yeah,
Is there wind on Titan, or?
there is wind. I don't know how fast the wind is. I tend to think of it more as a gentle breeze,
Oh, okay.
because it does have an extended atmosphere, very thick, but there is, you can imagine an environment very similar to Earth, I mean, you could hear a breeze, you could feel wind. It's just very cold.
Chilling.
Yeah.
So the illustrator didn't listen to our discussion about lightning.
There might be lightning on Titan.
Might just be sun peeking through.
Yeah, there could be the sun. But methane rain, fascinating.
I wouldn't want to be in that.
So we talked about this. If you look at a kind of a cross-section of methane, or of Titan, the majority of the lakes are forming in the northern part of the moon, and you got this one big lake down here in the southern hemisphere. Kind of interesting. So it's in a rainy season right now. It takes 30 years to go around the sun, so the rainy season on Titan is 7 years long. Gets back to your question. So that's probably why, we're not 100% sure, scientists are not 100% sure why all the lakes form in the north and there's only one down here. But it's probably because of the rainy season. You get some lakes on Titan that are as large as the Great Lakes. So this is the topography right now.
What's the axis of rotation of the moon with respect to Saturn and with respect to the sun?
The angle, the axial tilt, I don't know off the top of my head. I'll have to look that up. In terms of the plane of its orbit, it's in the same plane as Saturn's plane. It's a regular moon, which means it's following the plane that Saturn's path is around the sun.
But
It's in the
compared to Saturn's axis of rotation, what's the moon's axis of rotation?
I don't know.
Very similar.
It should be very similar, give or take a few degrees.
So the sun rises in the east.
Does the sun rise in the east?
Yeah.
And it sets in the west, yeah.
Except for Venus. Venus is
It's the other way, right? Yes.
How long is the orbit of Titan around Saturn? And I mean, does that have anything to do with the rainy season? That maybe when it's on the backside, on the, where, Saturn and is between the moon and the sun, that it gets colder at that time, then it starts raining. Then when it comes back around to the other side, that it gets warmer or something like that, and it causes vaporization or something?
It's not the rotation or the revolution of Titan around Saturn. It's where Saturn is
In conjunction to the Earth.
into the
I
sun.
mean, into the sun,
The
yeah,
sun.
okay.
So when Saturn is in its summer season, then you're going to have your rainy season on Titan.
Okay.
It has to do with where Titan and Saturn are relative to the sun.
Okay, I got you, okay.
I think it's 30 days is the time it takes Titan to go around. Yes.
Did this probe have a camera on it?
Yeah. Oh yeah.
Well, where's the image? I mean, do you, can we get them on the internet? Or?
You can. I didn't put them up here. I thought the visuals were more sexy than the actual images. To me, I'm a marketer, so it's all about what looks good.
Can you go back one slide?
Yeah.
There's an airplane up there.
I didn't tell you this. There's life on Titan. People living on
It
Titan.
looks like an airplane.
But Titan is a fascinating world because there might be.
That's where it is.
Scientists are still obsessed with this idea of finding organic compounds and the basic constituents for life, and Titan is a candidate.
We're methane-based life.
So life feels like the way it does to us.
Sure. There are scientists right now at the University of Denver who are doing experiments with the chemical constituents of Titan, and they shine light through it, and they're seeing organic compounds being formed, simple organic compounds.
If you're a methane-based life, then that heavy rain would feel like rain does to us.
Mm-hmm.
You'd get used to it.
You used to take a row.
They would be saying the same thing about Earth.
Yeah, imagine a life form on Titan looking at Earth saying, oh man, how can anything live in water? It's a very very reactive substance that dissolves things.
And it's
it would be like us looking at sulfuric acid.
It's thought for discussion for late night mixed drink.
Yeah. This is the kind of things we think about on a Friday night. We're astronomy nerds and everybody else is out,
Well, remember when Ballard found the fumaroles under the sea?
Yeah,
And they found stuff growing without light?
Yes,
Yeah.
extreme environments.
Yeah.
Extreme
So
files.
there's,
Extreme of what?
Extremophiles.
Extreme
Yeah,
files.
extreme files.
Extreme files. Exactly. So that's Titan. Fascinating world. I think it's one of the 7 wonders of our solar system. So again, Enceladus and Titan, why do scientists love these worlds? It's all about finding liquids, it's all about finding the water, it's all about finding candidates where you might have the basic constituents of life. So Saturn has a lot to offer. We've just scratched the surface, but I hope that this enhances your understanding. If you're like me, this Titan thing will roll around in your brain a little bit more. You'll be thinking about what would it be like to stand on the shoreline of a Titan lake when there's a gentle breeze blowing and you see this view of Saturn in the background. That just fascinates me. And it's not liquid water lapping up on the shore. It's liquid methane.
Really nice spacesuit.
Yeah. Yeah, exactly.
Really, really.
So some of these alien worlds are really fascinating in our solar system and bizarre. So that's it. That's my talk. Anybody have any other questions?
Quick one. Enormous scale of things, and the rings, but one of the sort of remarkable things is the thickness of those rings is 30 to 60 feet. Is that because the moons are so aligned to keep them planar, they keep them stretched out? And you have this vast scale of things, and that's compressed down to 60 feet.
I know, the rings are
Other
just,
than the mountain plane.
the rings are just incredibly,
Consistently thin.
yeah, they're incredibly fascinating because they're so thin and they're so well defined and they're such a beautiful feature to look at. I mean, it's really a miracle of nature, of science. So the best analogy I have to answer that question, again, getting back to the pizzeria analysis, where you have this clump of dough and you're throwing it up in the air. You know, if you watch a guy make a pizza, the more he spins it, the more it thins out. The more the dough thins out. The same thing is happening on Saturn with these rings. Because they're flying around the particles that make up the rings are moving so fast around the planet, they actually have a tendency to thin out and spread out. Same phenomenon, law of conservation of angular momentum.
It sounds like that, like those swing rides, if you were to take a swing ride and just crank it up, they would just go straight out.
Right.
Like,
Your angle is more vertical,
right.
and as your speed increases, you're being pushed out, right?
Right.
Flatten out. So. All right, guys, thank you for coming out.
Thank you.
That'll do it for us for this month. I'll see everybody next week. Next week, preach. Other session. I'll be there. Won't be there for Wednesday.
Well, it's hard to kind of like fix everything that's pretty great. We are stories like last year we
What I did, I'm sure this, I have an M number, and if it's anything else, like C, I have an E.
just there. As you were saying it, I'm like, okay, how am I going to sue, or, because it would be bizarre. Yeah, go ahead.
Yeah.
Send you some information. It's in November. It's like basically a 3-day event. It's running pretty short.
It's 4 things. I'm sending it to you.
Thanks for coming out.
that, I turn it like this, and I wonder why it was set to page 3, and then I might remember.
Well, next Saturday night, there's a flop.
Well,
And after that, they will send it to us.
Just send me whatever you want me to do.
All right.
Thanks, Richard.
Jeremy, J.E. was taken away from me yet, right?
Yeah, so Jeremy Veldman.
Once a month, the water, so what he's gonna do.
Jeremy's explaining on J.E.
I think you should stop.
Well, I was having a whole morning.
Yes.
And I hadn't heard anything from them, so I
Wait, let me stir up.
It's, no, you got it. Jeremy?
Oh, I was like, is there a phone?
It was hard to get them to be excited about it.
well, if I'm invited, I'll go.
Well, let me just tell you, if you're not listening there all the time, it's basically a 3-day celebration with science fiction. So.
Great to meet you.
Yeah, but you'll see, you come here walking around, there's a while, when they're just, superhero, like our guest of honor.
Well, somebody else has to.
Like SpongeBob SquarePants. And so there's like celebrity writers, but it's a party.
Without
There's
much
also
help.
this,
Yeah.
if you're an aspiring writer, you can network. As people find out about what's published, there's a lot of fun, but there's a lot of stuff with it being, science fiction. We also tap into the real, the real space science and all this. So I think it'd be, if I can email you this, you can, I'll send you flyers, I'll send you the whole website, but, the schools is really, what we're doing is we're taking all, we're taking superhero, science fiction fans, and we're using that, kids, we're just basically talking about those things, but we're showing kids the science. Whether so they're having a lot of fun, but they're learning a lot too, so what you're talking about, you will. I know what age groups you're comfortable with, because we have, junior high, we have a lot of
Started the.
So, now we do have some elementary schools, but this stuff with the Titans rolling, like you said, it was kind of going around my head. It may not even be Titan, but whatever. Something that we can really see what we're going to do is whatever, something we cover.
Village
Like,
Nice to meet you guys. See ya.
can cover in 30 minutes or whatever, but it's like, the idea is to get kids interested in this, or to get them excited about something, just really just kind of get their brain turned. And I don't know.